Welcome to the third section in the second part of our chapter on acid and base. And in this third section, we'll talk about the reactions of acids and bases, sometimes with just one acid and others of acid and a base together. And these examples you may have seen before in the laboratory, but we may have not described them as an acid or a base reaction. The first example is when we put magnesium into hydrochloric acid solution. Alright, so recall that we put a strip of magnesium metal, which is a solid, into a solution full of hydrochloric acid. It's a solution, so we put aqueous. Do you recall what the product would be? I will remind you then that it would be a single replacement reaction. So how do you predict a single replacement? Recall that from previous lectures. That magnesium metal will replace the metal-like cation here of hydrogen to bind now with magnesium and chloride. Now how do we write that properly as an ionic compound? Remember that magnesium is a 2+, chloride is a -1, so that is MgCl2. Right? So that was dissolved in water, so it stays as aqueous. And as a result from that, that hydrogen was displaced and it escaped as a gas. Alright, so let's quickly balance this as a review. It looks like I need a 2 there. Okay, so that's one type of reactions we've seen so far. Another one is a more canonical example of an acid-base reaction, where you have an acid reacting with a base. So for example, if I added HCl, which is your acid, and you add in base in there, NaOH. That is your base. What would we get? Now you want to think about this like a double replacement reaction or a double displacement reaction, right? So your metal or your cation will join with your anion, giving you that. And your cation on the other end will join with your anion on the other end, giving us this. Okay? So when you see an acid and a base, you can always do this kind of a prediction of what the product will be. Now let's clarify some things a little bit here. Remember that this is your polyatomic anion. It combines with your hydrogen, giving you your HOH. But what is HOH really? If we rearrange HOH, you can recall that that's basically H2O, which is water. Right? So in this kind of reaction, if you have an acid and it reacts with a base, it will always form this product. The first product is water. And the second product is what we call a salt. It doesn't have to be NaCl, it could be any ionic compound. We call that a salt. Another name for this type of reaction is called neutralization. Can you think of why we would call this a neutralization reaction? Let's think about what is the reactant. In the reactant side, we have an acid and a base. Right? But what's on the product side? Do we have an acid or a base anymore? The answer is we have water, which is neutral, and a salt, which is also neutral. This is the reason why this is called neutralization. You start with an acid and base, and you end up with something that is not acid nor base. Okay, so that is a prime example of an acid-base reaction. Let's have a checkpoint. Alright, here is another example of an acid-base neutralization reaction. So let's review some concepts here. Why is this called a neutralization reaction? Well, we start out with an acid, phosphoric acid, and a base. It has that OH, therefore it's a base. So acid and base, and what is your product? Your product is a salt of calcium phosphate and water. Right? So this, again, is a neutralization reaction. Now, the question here is to balance the equation. Well, when you balance an acid-base equation, it's very similar to balancing equations before when we have polyatomic. So using the same technique we did before, let's first list of all of your ions, including polyatomic ions, from left on what's on the left-hand side and what's on the right-hand side. So from here, recognize that H is your cation and PO4 is your polyatomic anion. Next we have calcium as your cation, and OH, hydroxide, as your polyatomic anion. Now let's do the count on the reactant side versus product side. Okay, on the left-hand side, you have how many hydrogens? We have 3. How many phosphates? We have only 1 phosphate. How many calcium? Just 1. How many hydroxides? It's in a parentheses 2, so we have 2 hydroxides. On the right-hand side, we have 1 calcium. Oh no, we do not. We have 3 calcium because of that 3 right there. How many phosphates do we have? 2 phosphates. Now remember, water can be written like this, or water can be written like funkily like that, right? So it's easy to see that how many hydrogens do we have? We have 1 cationic hydrogen. How many hydroxides do we have? We have 1. So I like to separate water out like that in balancing equation to make it easier when you have acid-base reactions. Okay, so let's do our accounting here. Let's just go randomly with the first one. To get this to be equal to each other, this must be increased, right? So let's increase this to 3, because 3 times 1 is now 3, and 3 times 1 hydroxide is also 3. I'm going to see that I will have a problem here already, but we'll just blindly go on forward. Let's go to phosphates. I have 1 here and 2 here, so I want to put a 2 here possibly. When I put a 2 here though, look at what happened. 2 changes the count of hydrogens I will have to become what? 2 times 3 is 6. That's going to change this in a bit, but we'll do this first, then we'll continue with the hydrogen. Since that 2 also goes into phosphates, now I have 2, making phosphates happy. So now, before we move on, let's just try to make hydrogen happy again. I mean, I want 6 hydrogens, but I only have 3 over here. So instead of 3, what should this number should have been? It should have been 6. Okay? So instead of 3, what's 6 times 1? 6. But remember, we also have to change OH count. So 6 times 1 OH is 6. Great, now I have 2 things happy. Now let's go to the third guy here. Calcium, 1 versus 3, so I need a 3 on this side. 3 times 1 is 3. 3 times how many? You already have 2 of this, now you have 3, so that makes it 6. Oh look, 6 and 6, hydroxide is also happy. So our final answer is 2, 3, 1, 6.